Welcome to this explainer. Today, we're totally flipping the script on how you view the night sky. We're going to decode the evolution of galaxies, but we're going to treat them not just as pretty static pictures, but as highly dynamic, self-regulating megastructures. Because these systems evolve over tens of billions of years, we're going to look at them through an engineering lens, really tracking their predictable mechanical life cycle from an active star-forming birth all the way to a quiet, evolved retirement. So let's just dive right into this.
Here's our structural blueprint for today. We'll kick things off with the foundational shapes, move into the active factories of spiral galaxies, observe the mechanics of galaxy collisions, examine the black hole thermostat, and finally, look at the closed system retirement of elliptical galaxies.
Section 1. The Cosmic Megastructure Blueprint. Let's start by looking at the foundational architecture astronomers use to categorize these immense systems.
To really grasp the mechanics of the cosmos, we first have to define a key term, and that's morphology. You can basically think of this as the engineering study of galactic shapes and structures. It's the framework we use to categorize the physical architecture of these megastructures, just based on their visual appearance.
Edwin Hubble brilliantly laid this all out back in 1926 with his famous sequence. It's colloquially known as the tuning fork diagram just because of its shape. Imagine starting at the handle of a tuning fork. That's where you find the elliptical galaxies, which range from perfectly spherical to highly elongated. Now, as you move down and the fork actually splits, we hit lenticular galaxies. Following the two prongs outward from there, we get to our regular and barred spiral galaxies. And finally, floating completely outside this whole fork structure, we have irregular galaxies. This entire sequence is our primary visual index for understanding galactic structure.
Section 2. Spirals, the active factories. With our blueprint in hand, we begin the active phase of the macrostructure life cycle.
For a long time, spiral arms presented a major mechanical puzzle for astronomers. It was called the winding problem. You see, if the inner stars of a galaxy orbit faster than the outer stars, which, they do, then if the spiral arms were solid, rigid structures, they would wind up tighter and tighter until they just completely disappeared after a few orbits. But they obviously don't. To explain why these structures persist, C.C. Lin and Frank Hsu proposed the density wave theory in the 1960s.
To really visualize this, think of a spiral arm exactly like a massive traffic jam on a highway. The jam itself, that area of highest density, moves pretty slowly. But the individual cars, which in this case represent the stars, gas, and dust, they speed into the jam, slow down while they're stuck inside it, and then speed right back up as they exit. So the arms aren't actually made of the same permanent material at all. They're self-sustaining waves of density.
So, let's trace the mechanics of this active factory. Raw materials, like these sprawling clouds of cold hydrogen gas and dust, casually enter the density wave. When this matter hits the traffic jam, it gets highly compressed. And this intense compression hits the threshold for gravitational collapse, which suddenly triggers fierce, energetic bursts of massive new star formation. It literally lights up giant regions with hot young stars. Eventually, the older, smaller stars and whatever surviving gas remains speed up and exit the wave, keeping this continuous mechanical loop of the active factory humming along. Depending on differential rotation speeds and localized star formation rates, these active factories can actually output a few different structural patterns. On one hand, you have grand design spirals, and these feature two perfectly well-defined, continuous arms. It's what you typically picture. But on the other hand, you have flocculent spirals, which have a much patchier appearance made up of many small, discontinuous arm segments. And our own Milky Way? It's actually a mix of both types.
Section 3. Collisions, a gravitational dance. What happens when two of these active macrostructures cross paths?
Now, when we hear the phrase galaxy collision, we naturally picture a violent, fiery demolition derby. But here is the absolutely crucial point. Because the distances between individual stars are just so unimaginably vast, actual stellar collisions are practically non-existent. There's almost zero chance of two stars hitting each other. Instead, a galaxy merger is an incredibly elegant, fluid, gravitational dance spanning millions of years. The overarching structures warp and stretch, but the individual stars themselves, they just safely pass right by each other.
However, while the stars don't hit, the vast, sprawling clouds of interstellar gas absolutely do. As these immense gas clouds smash into one another, they send massive shock waves racing through the structure. These shock waves compress the gas at incredible scales, resulting in what we call a starburst. It's a ferocious, sudden burst of massive new star creation that goes way, way beyond a galaxy's normal output.
To give you a sense of the scale here,
Look at the merging system known as NGC 3256. In this colliding macrostructure, the stellar feedback pressures, which is the immense energy, shock waves, and stellar winds pumping out from newborn massive stars, are roughly 100 times stronger than what we see in a normal isolated spiral galaxy. 100 times! And it's exactly this feedback that shapes the continuing evolution of the entire merging system.
Section 4. The black hole thermostat. If these factories have all this gas to make stars, how does a galaxy eventually turn its manufacturing process off?
The answer to that is hiding right at the absolute core of the structure, within what astronomers call an active galactic nucleus, or AGN for short. This is an incredibly compact and luminous region powered by a supermassive black hole that's actively accreting, or basically just rapidly eating, massive amounts of surrounding gas and matter.
Now, you might be wondering, how in the world can a tiny central point dictate the fate of a megastructure that spans hundreds of thousands of light years? Well, we know this central engine is intrinsically linked to its host structure because of a fascinating mechanical property called the M-sigma relation. This is a strict mathematical correlation that ties the mass of the supermassive black hole directly to the stellar velocity dispersion, which is basically the speed of the stars in the galaxy's central bulge. They literally evolve together as a single system.
Let's see how this builds into a perfect, self-regulating galactic thermostat. As that central black hole consumes excess gas, the intense friction generates immensely powerful, high-energy jets and radiation. These huge outflows physically sweep up and drastically heat the surrounding interstellar gas. And because the gas is now way too hot and turbulent to gravitationally collapse, star formation is completely choked off. The factory shuts down.
And we have the solid data to back up this negative feedback loop. Recent 3D spectroscopic mapping, especially focusing on galaxies at the cosmic noon epoch when star formation was at its absolute peak, really proves this mechanism. Observations show that galaxies hosting powerful AGN winds have molecular gas fractions that are 3 to 10 times lower than their quieter counterparts. But even more striking is the spatial anticorrelation. That simply means star formation is visibly suppressed exactly in the physical locations where these powerful outflows are blowing through the galaxy. It's incredible to see the mechanics working in real time.
Section 5. Ellipticals. The retired power plants. Which brings us to the final, post-manufacturing stage of our macrostructure life cycle.
Once that central black hole thermostat forcefully shuts down the factory, the entire system undergoes a massive transition. We move from an active spiral galaxy, which, remember, is a gas-rich open factory producing young, hot blue stars, into an elliptical galaxy. And this new state is a closed system. It's gas-poor, lacking the raw materials to build anything new, and it's illuminated only by the faint glow of older red stars.
Because these structures lack the cold hydrogen required to build new stars, astronomers colloquially call these systems red and dead. They're essentially retired power plants, just coasting purely on the aging, low-mass stellar remnants of their highly active and often very violent youth.
It's worth noting, though, that these retired megastructures are actually in the minority overall. They represent only about 10 to 15% of galaxies in our local Virgo supercluster. Because many of them are actually the end result of multiple past spiral galaxy collisions, you're typically going to find these massive ellipticals resting quietly in the very dense, crowded centers of galaxy clusters.
Understanding this totally predictable life cycle, from a swirling active spiral to a red dead elliptical, leaves us with a really profound realization. Our very own Milky Way is currently an active factory, complete with density wave traffic jams and ongoing star formation. But we are on a collision course with the massive Andromeda Galaxy. Billions of years from now, our galaxies are going to merge. The shock waves will trigger a massive starburst, and eventually, that central thermostat is going to shut the whole system down for good. Our dynamic home will become a retired elliptical megastructure. So, what kind of new cosmic phenomena might arise from the ashes of our current galactic factory? I'll leave you to ponder that one. Thank you so much for joining me on this explainer, and as always, keep looking up.